Good evening. In this video, we are going to discuss both Proposition 12 and Proposition 13 from Book 2 because they are similar. So first of all, let's talk about Proposition 12. And please allow me to skip the Euclidean construction steps for convenience. And this proposition declares that if we are given an obtuse-angled triangle, for example, ABC and C is the obtuse angle, okay? And let's at first do some construction. So use postulate 2 to produce AC, and then use proposition 12 from book 1 to construct a straight line through point of B that is perpendicular to the produced AC. And let's assume they are meeting each other at the point of D. Okay, so we have completed the construction. And the proposition states that the square on the side that is opposite to the obtuse angle, which is C square, is greater than the sum of the two squares on other two sides by twice of the rectangle contained by B and D, where B is a side that contains the obtuse angle and D is a straight line that we have constructed like that. Okay, so let's give it a proof. So first of all, please recall proposition 4 from book 2. It declares that if a straight line is cut at a random point, then the square on the whole is equal to the squares on both segments together with twice the rectangle contained by two segments. So we can see that AD is a whole, and let's assume C is a random cut point. So we have the whole is AD square. It is equal to the two squares on two segments plus twice the rectangle contained by them. Okay, so this is the first equality. And if we apply proposition 47 from book 1, we have A square is equal to D square plus the square on BD in this right angled triangle BDC. And if we apply it again in right angled triangle BDA, we have C square will be equal to BD square plus AD square, correct? Okay, and in the next step, let's plug in these two equalities into the first one. So we have that AD square here, so let's plug it in. Then we have C square minus BD square will be equal to this, correct? And then let's plug BD square, plug in here again. So we have C square minus BD square will be A square plus D square will be equal to the right side. Sorry. And if we simplify this equality, we will conclude that we can conclude this equality, correct? And this is absolutely equivalent to the given proposition, correct? So we have proved it. And then let's move to proposition 13. It talks about exactly the same thing, but in this case, it focuses on an acute-angled triangle. So let me skip the construction steps again. In here, we just use proposition 12 from book 1 to construct a straight line through the point of D that is perpendicular to AC, and they are meeting at the point of D, okay? And the proposition states that if we are picking up any kinds of acute angle in this triangle, for example, angle C, then we have, let's say, the square on the opposite side is less than, so less than will be this, less than the square on two other sides by twice of the rectangle contained by a side and D. And D is a straight line that we have described how to construct, okay? So it declares this equality, and let's give it a proof also. The steps are absolutely similar to proposition 12. So first of all, let's apply proposition 7 from book 2. So it declares that if a finite straight line AB is cut at a random point C, then the square on one segment together with the square on whole will be equal to twice the rectangle contained by the whole and this segment together with the square on another segment. Okay, so let's apply this here on this finite straight line AC and assume D is a random cut point. Okay, so we have what? We have AC squared here. So let's say the segment, the square on the segment together with the square on the whole will be equal to twice the rectangle contained by the whole and this segment, which will be twice BD together with the square on another segment. Here it will be the square on AD. Okay, then let's apply Pythagorean theorem twice on these two right angle triangles BCD and BAD. So we have A square will be equal to the square on D plus the square on BD. And we have C square is equal to the square on AD plus the square on BD, correct? And then very similar to the previous step, let's plug these two equalities in the first equality. Then what do we have? We have, let's at first plug AD here, AD square here. So the left side is equal to correct? Because we plug this here. And then let's plug in BD square here. So we have the left side is equal to minus BD square will be A square plus D square. And if we simplify this equality, we will have that A square plus B square is equal to twice of the rectangle contained by BD plus the square on C. And this is equivalent to the proposition we are trying to prove, correct? So we have proved the proposition. Okay. So proposition 12 and 13 have been successfully proved, but I would like to introduce a bit about the law of cosines because it can summarize all of these two cases as well as even proposition 47. Okay, so while Euclid was writing this book, The Elements, the terminology or the concept of trigonometry has not been developed or has not been invented yet. So Euclid had not used the concept of, for example, sine, cosine, and something introduced by trigonometry. Okay, but if we think about the law of cosines, it declares that remember, in any kind of triangle, it is, no matter it is obtuse, acute, or right, we always have this equality. So C square will be equal to A square plus B square minus twice of AB times cosine C. Okay, this is the law of cosines. And we think about these two specific cases, the obtuse-angled triangle and acute right-angled triangle. We can see here, we have that, this is our conclusion, correct? We have C square is equal to A square plus B square plus twice of BD, correct? And let's write cosine C by, we can see that C is an obtuse angle, correct? So cosine C here is equal to negative D over A, correct? It is larger than pi over 2, so the cosine of this angle is a negative number. So if we plug this in here, we have that it is, oh, I'm sorry, let me write it in this form. So we have D is equal to negative A times cosine C, correct? And if we plug D in here, we have that A squared plus B squared plus 2B times negative A times cosine C. And we can see that this equality is absolutely equivalent to the law of cosines, correct? And we can do the same thing in an acute angled triangle. So here, let's assume this is angle C. So cosine C is equal to what? Equal to A over D, correct? And so D is equal to I'm sorry, that's my bad. It's equal to D over A. So D equals to A times cosine C. Okay, and if we plug in the value of D to the conclusion of proposition 13, we will have that A squared plus B squared is equal to twice of B times A cosine C plus C squared, correct? So if we do some algebraic manipulation, we will conclude that C squared is equal to A squared plus B squared minus 2AB cosine C. Okay, so they are absolutely equivalent to each other. And sorry, in addition, if we assume angle C is equal to a right angle, and in this situation we are talking about a right angle triangle, so cosine C will be equal to 0, and in this case the law of cosines here, since this is 0, will be simplified as C squared is equal to A squared plus B squared, which is equivalent to proposition 47 from book 1, which is also known as Pythagorean theorem. So Pythagorean theorem is, to be honest, a specific case of law of cosines. Okay, so that's a brief introduction about law of cosines in trigonometry, and that's it. And in the next video we are going to discuss proposition 14 from book 2, which is the last one from book 2. Okay, thanks for watching, have a good day.